Welcome everyone to the second talk of the day, and it will be on how to build high quality AI models in healthcare with small data. Now, as you're probably aware, increasing demand for building high quality models is challenging due to the paucity, regulation, privacy concerns, and need of expert data. In this talk, Dr. Ravindra Patil will be covering how high-quality AI models can be built with very small amounts of data. So without further ado, I present you Dr. Ravindra Patil, the Group Leader and Senior Engineering Manager from Philips. Enjoy the talk, and afterwards I'll be back with the question.
Thank you, Anden. Great. Thanks for having me here. I'm Ravindra. I'm Group Leader at PH Data and AI team. And today I will be discussing on some of the aspects on the challenges of building a high quality AI model, very particularly to the domain of healthcare, right? And how we can overcome some of these challenges and what are the technical enablers that we can leverage such that this barrier of having the data to build a high quality AI model could be lowered. With that, let me jump on to my presentation. If you take a step back, right, in case of a generic AI model, the ImageNet challenge stands out, right? And then over the years from 2011 till 2020, there has been a significant progress in terms of the amount of accuracy the models were able to improve from the classical machine learnings to that of deep learning. Although this is kind of attributed towards two factors. One, we said the compute power now that is currently available is significant, and there are new neural network architecture which are too good to find the underlying pattern that's helped improve this accuracy on this test data. But I'd also argue and say it's not only those two, but it's also about the right quality of annotated data that was made available to benchmark these kind of challenges. Assuming if there are no 1,000 classes and millions of hand annotated data set of ImageNet it was, so it would have been quite difficult to leverage and prove the efficacy of all the newer models that we have seen from few years that we are seeing in the era of deep learning currently, right? So the question that I have is following. Do we have this luxury in healthcare with respect to data? Is it possible to have such a kind of massive data being available such that a high quality models could be built? To put to the perspective, if you see some sample publicly available large medical imaging data sets, for example, on your left, you could look at the deep lesion by NIH, right, containing the CT. There are close to 32,000 images that are annotated. Chest X-ray, the RSNA, ICH detection data, close to 25K subject images, and the chest X-ray, right? So 200K. So if we compare this data size with that of what we saw earlier with ImageNet, there is a significant parity about the amount of data that is available to build high quality AI models. And this we need to live with it because of all the restriction that comes and the regulation aspect that comes with respect to medical images, or the medical data itself. If that is the case, we also want to look at a bit and say, what's the typical timeline for development of an AI model from ideation till we deploy the model, right? If you roughly put it across into a time horizon that you're able to see it on the screen, the time required for hypothesis on what is a problem statement definition, it would roughly take around 2 months to ideate. Then it goes into the clinical site identification for finding the right partner, then going across for the ethical approval and the collection of the data later on to build and validate this model. In this entire chain, the maximum amount of time that is spent by a data scientist or the stakeholders who want to realize the AI model development to production is on the ethical approval and the collection of data, right? So one of the barrier to speed the things up is to ensure how can we quickly navigate this and then ensure the throughput is better. However, that's not always the case. Right? There are some genuine concerns why it takes some of this time. If you look at those, this could be following, right? The one of the challenge itself could be the administrative in nature because they don't have ability to provide the required resources to make this happen. The other might be political in nature, where what is in it for them to share this data, right? The third being the ethical concern, because most of this data belongs to the patient, we don't have any rights to consume, in spite of the consent being obtained. The other could be also on the technical front, where there are no two systems which can talk to each other. There is no synchronized API fashion where the data could be extracted. All of these different systems might be lying in their own silos, and technically there are no resources to put across such that these data sources could be connected or collected to build these kind of AI models. And obviously, there could be also the commercial agreement that would come in. With all these being the barriers for sharing the data and this being the timeline for development of any models on an very classical way, the question that we put across is, can we reduce the data access time leading to an efficiency gain in development of these models? To address this, one of the approach that we took was a combination of hybrid AI, active learning, and federated learning to build these kind of quality AI models. And there are some amount of benchmarks that are done. If we use this approach versus not using this, how much is a difference that we see? So my next set of slides would typically cover this gamut of combination of hybrid AI plus the active learning and the federated, and how could we evolve this technical enablers to ensure we get the high quality AI models, although with a limited data set that's possible to collect. So before going into each of it, if you take a traditional AI approach as it is moving now, it's more towards providing the large heterogeneous data to this model such that they learn the underlying pattern. So more the variety of data, more the amount of heterogeneity that is added to the pool, that's how better the AI model gets by understanding the underlying pattern. This is more towards a data-centric AI way of doing things. However, as we said, the luxury in the healthcare is the data itself, and that too the high quality annotated data. Hence, what we say is it's more than AI, it's more than just applying the data to the model, but it is more about taking a little of a deviation than just applying the data, but using the approach of hybrid AI. It encompasses the following for us about ensuring that the data is rightly pre-processed for the noise removal, the background subtraction, the artifacts removal, such that the amount of ambiguity that is already exists within the data for the intended use case is reduced such that the model can clearly focus on the patterns that it wants such that the decisions could be made. Other thing in the healthcare is there's a lot of anatomical intelligence that is available. For example, we do know where the lung is and what's the relation between the lung and the other organs, how far it is, right? What is the structure of a lung and a liver, such that can these anatomical structural intelligence be leveraged in some of the processing? Either it could be a segmentation or for a classification. Can these anatomical intelligence could be exploited and sent as a and the signal channel within the model such that it becomes more intelligent? Third is also embedding the models with the right clinical knowledge. Years of study is spanned to ensure that a clinical uh, practitioner or a radiologist tries to assimilate over the course of their career the different clinical knowledge that they bring in, is it possible to embed some of these clinical knowledges within the models such that all the corner cases or where there is ambiguity that can be reduced, right? So embedding of the clinical knowledge is also one of the approach that we take in case of the hybrid AI. Not only that, it's also about the synthetic data generation and capability to augment the existing data such that can we vary the texture of the tumor within the image that we have collected such that we can get within the the normal boundary of how it can, but can there be a variations that could be generated such that it can add as a new data for the training for the model such that the amount of bias or the accuracy, right, is the bias being reduced and the accuracy being increased by augmenting this with the right kind of synthetic data. So if you combine all these three plus the generation of the data is what we call a hybrid AI before the data is being fed directly to the AI model training. In order to make it into a concrete example, right, does it indeed it works? Let's take an example of one of the work that we did on the stroke hemorrhage detection. So if you look in the stroke as an area, there are two kind of detection. Either it could be an ischemic or an hemorrhagic, where whenever an artery ruptures and then there is a flow of blood, as you can see on the screen, the white patch is what has get manifested on a CT scan whenever there's a hemorrhagic stroke. Now, if you take the simple example of how this could help build an AI system which can take in or ingest the large volume of CT images and finally provide an output saying whether there is a hemorrhagic stroke or not. If you look into the hybrid principle, it was all about adding the anatomical intelligence, knowing the clinical knowledge, then also augmenting it. And that's what you see on the screen. Here, the entire CT image that was taken, we removed across the skull that was available, remove the bones that are present because the structure of the bone when it is seen, it also looks like a white patch, and which also resembles that of a stroke region, right? So how it's possible to remove all the artifacts which could be kind of confusing to the model by using some of the anatomical intelligence that is available? Can we do the scatter compensation because whenever the x-ray hits the broad region of the bone, there is a small amount of scatter, and this scatter also manifests as a white patch. And is it possible for that to be eliminated such that the data that finally goes within the model training is already pre-processed to an extent that most of the ambiguity could be removed? Then the other is also about, is it really a need to send all the slices together? If the use case is about detection of a hemorrhage itself, it's good enough to make sure the entire CT slice are being compressed together to form a maximum intensity projection such that we only worry about whether there is a stroke in the entire CT volume or not. And then you do a maximum intensity projection. So this component within these blocks are all the hybrid approaches before it goes for the trained DL model. Finally, it spits out whether it has a hemorrhage, non-hemorrhage, or if it's not possible to characterize, can it give across this label as cannot be characterized. So this is one of the approach within the hybrid AI concept. Now, to test it, whether it indeed works or how does it compare with a traditional AI approach where we have this data and then tune a model to one of the architectures and then see how the efficacy of it is. So to prove this hypothesis, we had trained data of close to 379 subjects, and 79 subjects were kept aside for a test as a golden ground truth. Now we use a model of modified inception ResNet V2, and with just application of a data to the same model, those are the numbers that you see on the screen in terms of accuracy, sensitivity, and the specificity. But if you apply the same concept with respect to the hybrid AI approach, those are the numbers that you are trying to see, yeah? Which is almost close to 0.90, where we are able to come closer to the radiologist knowledge and understanding of how the stroke can be classified. So with a small change in the approach of not just putting the data directly, but using the concept of hybrid AI, we could exploit that to bump up our accuracy numbers. Now, the second challenge is also about getting the right annotated data for us, right? And the challenge with annotation is twofold. One is amount of time that is required to do so, and the second is a resource. And here we are talking about the trained people who have the limited time at their disposal, unlike the normal computer vision problem where people with some amount of training can still go ahead and annotate. Here, we need a specialized skill people to annotate some of this medical pathology. Now, coming to this question, how can we prioritize the data which needs to be labeled in order to have the highest impact to the training? So in essence, what we are saying that is it possible to take into account only those images that have high impact for the model to learn such that we are able to improve the accuracy rather than passing on every data point that we get to a trained radiologist or a clinician to do it. And we leverage a concept of active learning here. The proposal here is you do have a seed data, the hybrid AI model that was learned in the previous slide that you saw. And this AI model runs on all the unlabeled collected data pool and try to identify from this unlabeled data pool which are the data samples which are ambiguous in nature, where the model is not able to make any decisions. And only those data samples are sent back to the oracle, or what we call it a skilled physician, who takes a look at it and then it again comes back to the cycle. So it helps us solve two major problems here. One is about we don't overwhelm the physician to see every data sample that is passed through, but only the critical ones, which is going to add more value to the model, or where the underlying pattern is so different that the model has earlier not seen. So those are the only data sample that goes to the oracle, and then we consider them for retraining of the model, and this cycle keeps continuing till the time there are no ambiguous cases and model get matured. So this is one of the concepts that was adopted in order to see is it really worth trying this approach. Then there was a comparison that was carried out between an active learning concept to that of a normal learning. For that, this is how the data distribution looks like. You have 379 initial data sets that we said. We built an hybrid AI model. Then there were 6,000 subjects which were outside of the scope, which were divided into training data of 5,000 and 1,000 test data. With this kind of data distribution, if you use a traditional deep learning normal approach where you already have a seed model with this kind of 379 samples, this was the accuracy that you got, then you try to do a transfer learning on the remaining 5,000 data set that you had and run it on your test data. These are the numbers that you were able to attain. In this case, all the 5,000 data samples were used for the model training. However, in case of an active learning approach, you don't use the entire 5,000 for it, but only the subset of this are being fed to this model. And we found that there are only 555 ambiguous cases which were good enough for the model to learn something new, right? Only these 555 cases were again went for re-annotation. In this case, already the labels were known. And then this process keeps continuing till the time the number of ambiguous cases got reduced. Now, if you see the final model of the active learning cycle, this versus that of the original model that it learned on consuming the entire 5,000 images, it was able to come closer to the same numbers. So what we try to infer out of this is with the active learning, there is kind of possibility to reduce at least 80% of the effort in the data annotation also it depends on kind of use cases they are working on. At least for this use case, that was the case, wherein you no need to annotate every image that is there in your data pool, only identify those significant ones where a model has an ability to learn something new, and that would lead to a significant reduction in the annotation effort, which internally leads to the reduction of the time that goes from ideation till the deployment. With that being solved, or to a certain extent understood about how can we improvise the annotation, the second aspect is about the sharing of the data itself. And we saw some of the challenges in the earlier slide, but if still those challenges remains, what is the other approach? It's about, is it possible if the data can't be pulled into the premise to build a model? Is it possible that the model can go back to its own premises where the data resides such that the model can learn, which is all about the federated learning approach. So here you have your hybrid AI plus active learning. That's what you saw in the previous slide. This model was taken into account, and this model was dispatched across to virtual hospital nodes, and the model tried to learn within this own hospital environment, and the weights of these models were shared across, right? So these model weights were shared, which was used to build a global model which had an ability to kind of have a representation of all the underlying different variations. So the idea here is, if there is a barrier for sharing the data, the other approach is to deploy these models across the different institutions where it has an ability to learn and the global models could be there. Now, the question also comes in, how good is the accuracy of the models when we just combine these weights and then try to build a global model? In order to do that, this was also an activity that was put across wherein the entire data set was taken into account, and then we try to merge this data all together at one side and try to see what is the efficacy of the outcome, and when this data was in the virtual nodes, how was the performance. If you look at it, it was a two-node problem. That's how we did, and then simple averaging of weights, and we could see the accuracy at the node 1 and node 2 are following. When the merge model was used, it was somewhere around 0.92, and when we had the data which was all together in the same system, almost we are able to get back to the same level of accuracy. So at least this concept of federated learning, where there is challenge of accessing the data, could be leveraged such that you can improve the model and improve the performance of the same. With that, I kind of come to the end of the presentation, where wish to highlight that it's less is more. The combination of hybrid AI, the active learning, and the federated approach helps achieve build high quality AI models with less data. And we could see it based on the sample data and the use case of a stroke that we saw in the previous slides. However, the only caveat is about the seed models that you create are of high quality or a good one, such that it doesn't add biases down the channel. So with that being put across, it helps, this combination helps us do following three things better. One is faster. Can we build a diagnostic AI model faster than just putting across all the data in a single rack and then trying to train? The second one is, it's cost efficient. You don't need to buy the entire data that you need, but only you can pick and choose which kind of data that will add more value to the models. Only those could be pursued. A third is a better high generalized model with the federated learning. When you have these institutions or the source of data that are across the geography, the kind of heterogeneous mix of different parameters that comes in adds to a better generalizability of the model. So with that, I summarize saying, although we do have significant challenges in healthcare with respect to the access of data, although for the right intent, but some of this could be overcome with this combination of three technical enablers of hybrid AI, active learning, and federated approach. Thanks for listening in. And that's the end of my talk. Thank you.
Thank you, Ravindra, for this exciting talk. We do have a few questions, at least one for now. The question is, we talked about a bit about the difference between the normal AI model and the hybrid model, but for companies that are deeply entrenched in the normal one, could you elaborate a bit more some of the challenges you foresee switching from one to the other?
Thanks for the question. Indeed, some of the challenges would be about the domain knowledge that is required to build these hybrid models, right? So it takes a lot of efforts to understand the underlying pattern and the domain knowledge associated with the use cases. So it would take some amount of effort in terms of resources and the time to understand that underlying domain. So if that is taken care, then the kind of transition from normal to the hybrid should be smooth.
Thank you for that. And sticking with the issue of this change, you talked about biases, especially when it comes to the original sets of data and the normal one. So is it possible to account for them in the hybrid model later on a bit, trying to adjust them for the biases, or is it important to fix the data at the very start and then you cannot do it afterwards?
That's a very good question, right? So the hybrid model indeed has to take into account the bias at the start. Otherwise, it kinds of derails. So the amount of your test pattern or your test set that you try to build in should be good and the robust enough to take into account some of these biases. Although you can go back and correct the hybrid AI model later, but it will be a little late. So getting that first time right is crucial a bit here.
And a final question is, could, in your opinion, what is the, not just for this model, but what is the optimum amount of data one should have when training the hybrid model or the normal one as well?
I don't have any ballpark numbers, right? So it's on the use cases, that is, but typically it is for per class. That was a rule of thumb. 5,000 samples should be there for each of the classes that you are trying to predict, right? So that's what some of the heuristics that are there in the literature, but nevertheless, it is a trial and error. There is no clear way to say that these are the total number of data samples that are always required. It also depends on the quality of the data and the kind of heterogeneous nature of the data. But ballpark, it's per class 5,000 helps us to navigate forward to build some good quality AI models.
Okay, that's it for the questions. Thank you once again for the talk. I'm sure you gave a lot of people a lot of insights to think about and potentially utilize the hybrid models. And on behalf of the conference, I thank you once again for attending.
Thanks for the invite. Thank you.